Let's see how waves can be created. It is said that when something about the physical world changes, the information about that disturbance gradually moves outward, away from the source in every direction. What does that mean? Let's take a bowl with water, and in it we've placed randomly pieces of paper. And you will create this kind of disturbance by placing your finger inside. We know that waves will start to form, and these waves will start to move outward in all directions. Now the thing here is that we will ask ourselves, will the piece of paper move along with the wave, or they will stay in place? And you can see that the piece of paper is actually only vibrating or oscillating in place. You can see that the piece of paper is moving upward and downward, but not moving along with the energy of the wave. So what we can say is that the waves is an oscillation or a vibration that transfers energy from one place to another without a physical transfer of any material between the 2 points, which means that it's only the energy that is transferred and not the matter. And it moves outward, as we saw here. So after you create the disturbance, the wave will start to move in all directions and in a periodic way. Alright, so the basic of waves are: when we make the oscillation upward and downward, this will create a sort of a transverse wave. So that's the first type of wave that we know. When the oscillation is upward and downward, keep in mind that the energy is always transferred forward. This is called a transverse wave. Okay, so if you focus on the green ball, you can see that the green ball is actually oscillating. Okay, let's see. It's oscillating in place. It is not being transferred. And this will also help us to understand that it's only the energy that is transferred, but never the matter. All right? Now, if we take the oscillation and the energy transfer, you can see that they're making like a 90-degree. That's the energy transferred, and that's the oscillation upward and downward. They're making a 90-degree angle between the energy transfer and the oscillation. Second type of wave would be when you will start to vibrate your slinky side to side. Okay, so vibrating it side to side means that you're creating a longitudinal wave, which once again, if we focus on the green dot, you can see that the green dot is oscillating side to side. In such case, we say that the oscillation and the energy transfer are said to be parallel to each other. And so this is a transverse wave, and that's a longitudinal wave. In a transverse wave, we will have a crest and a trough. In a longitudinal wave, we can have a compression and a rarefaction. This is a rarefaction. Okay, and that's a compression. We have many examples for transverse and longitudinal wave. So if we focus on the guitar example, because usually students, they are so confused about the guitar example. You can see that the vibration of the string when you pluck the guitar is a transverse wave. So the movement of the strings of the guitar is transverse, but when it comes to the sound produced, the sound is an example of the longitudinal wave. Pause the video and match each label in a correct position. Both longitudinal and transverse wave, they have the following features. They have an amplitude, a wavelength, a frequency, and a period. It is easier to see these features on a transverse wave. So I'm going to take a transverse wave as an example and show you where can we find these features. This is the rest position. Rest position is the position where the particles are still undisplaced. The rest position is the position where all the particles are not displaced yet. Alright, so if let's take two particles over here. This particle will go up to the maximum position, which is called also a crest, and this particle will go to the minimum position, which is also called a trough in a transverse wave. Okay? If you compare these two arrows, you can see that they're actually equal in size. That's because a wave will always have a fixed amplitude, and it's kind of pattern that repeats itself over and over again. An amplitude represents how much energy the wave is carrying along. As for the wavelength, let's see now if we compare the distance between two crests and the distance between two troughs, or the distance between any random 2 points on the graph, you can see that this distance is constant, it remains the same. Look, it keeps on showing us that all these distances are the same. This is called the wavelength of the wave. That's because it shows us the length of one wave. So one wave is made out of what? One wave is when we have one crest and one trough together. This is where we know that we can count one single wave. Okay, now let's go for the frequency. And let's consider we have these two waves below, wave A and wave B. And let's consider that we have a stopwatch and we're counting in 1 second how many waves are passing in A and how many waves are passing in B. Remember that one wave is one crest and one trough, or we can start with one trough and one crest. Okay? So, starting from here, that's one wave, 2, 3, 4. So wave A has 4 waves going each second. As for wave B, starting from here, this is 1 and this is 2. So in wave B, we have only 2 waves going each second that we're counting. In fact, what we just found is called the frequency of the wave. It is a way to count how many waves go through a specific position each second. And instead of using waves per second, we can use the unit for frequency, which is hertz. So what we can say is that wave A has a frequency of 4 hertz, wave B has a frequency of 2 hertz. Now, let's compare the wavelength, which is the distance between crest and crest, or trough and trough, of wave A and wave B. We can notice that if we compare both of them, we can notice that the wavelength of wave B So wavelength of B is much greater than the wavelength of A. Now if we compare the frequency, we can see that frequency of wave B, which is 2 Hz, is smaller than the frequency of wave A, which is 4 Hz. And this shows us that frequency and wavelength are inversely proportional, which means that if we increase the frequency of a wave, then the wavelength will definitely decrease. In fact, there is a relationship that can link both the frequency and the wavelength in one formula, which is this formula. We can find the speed of the wave by multiplying the frequency by the wavelength. So in fact, if we rearrange the formula, let's say I want to get F equals to what? It's going to be V, velocity, divided by the wavelength. And this shows how frequency and wavelength are inversely proportional. So let's take this example. Calculate the speed of the wave that has a frequency of 90 Hz and it has a wavelength of 3 meters. That's a direct application. You will say speed is equal to the frequency, which is in Hertz, so 90 Hz, multiplied by the wavelength, which is 3, and we will get an answer of 270 meters per second. Now for the last feature, period and frequency are actually related to each other. Period, it tells us as a definition, if we return back to the definition, it's the time taken for a full cycle of the wave to be completed, and it has an SI unit of seconds. So in order to find the period of a wave, we need to divide 1 divided by the frequency. Let's take this example. Calculate the time period of a wave with a frequency of 50 Hertz. So by a direct application, you'll say period T is equal 1 over F. It's 1 over 50, it's 0.02 seconds. Or sometimes the period is given and you have to get the frequency, and by a simple calculation you will say that frequency is 1 over T, 1 over 0.8 seconds, that's 1.25 Hertz. Now how can this relationship help us in order to find a second relationship for speed? So we can substitute in the formula V is equal lambda times F, we can substitute F by 1 over T, okay? And then we can have the new relationship, which is V is equal to lambda divided by T. And so you end up with this triangle, and this one. Sound wave is an example of a longitudinal wave, which means that the vibration happens side to side or back and forth. That's the oscillation. So in fact, when you talk, what you're doing is you're sending a type of energy that is transported through the air particles from the source all the way to the ear of the receiver, or like to the surrounding. So in fact, this vibration cannot happen unless we have particles involved, whether they are solid, liquid, or gas. So in order for a sound wave to be transmitted, a medium is needed. Without in a vacuum, without the presence of any particles, sound cannot travel, cannot be transmitted. And this is the reason why in the outer space, astronauts cannot hear each other if one of them is talking. So if we think about now the three medium that we have, solid, liquid, and gas, and we think about the idea that sound wave needs particles in order to be transmitted from one place to another, then, logically speaking, the closer the particles are to each other, the faster the transmission will happen. And the further away particles are from each other, the slower this transmission will happen. And this is why sound wave travels the fastest in solid, and then in liquid, and then in gas. This is a table that shows the speed of the sound in different medium, like aluminum, glass, seawater. What we mostly use, and you need to know, is the speed of the sound in the air. Now let's see what affects the volume of the sound. So when we turn our volume down or turn it up, what are we actually doing? Which feature out of the feature that we took we are actually changing? If we compare two sounds, one that is soft and one that is really loud, let's start by comparing the features one by one. All right? So I'll start by comparing the wavelength, which is the distance from one crest to another or one trough to another. You can see that the wavelength remains the same. So wavelength is the same. Let's see now the number of waves that are going per second, which means that we are finding now the frequency. So that's one wave, that's two waves, and that's around half. Here, that's one wave, two waves, and that's the half. So in fact, frequency also remain the same. So what is changing then? And considering that they are both in the air, so they will both be traveling with the speed of sound in the air, which is equal to 340 meters per second, thus speed will also remain the same. So the only thing that is different between this diagram and this diagram is actually the amplitude, the displacement of the particle from the rest position all the way to the crest or to the trough. You can see that the higher the amplitude, the louder the sound. The lower the amplitude, the softer the sound. What about the pitch of the sound? So once again, we will compare the features. All right, so let's start by comparing the wavelength, crest to crest, or trough to trough. I'll take crest to crest. You can see that wavelength is changing. All right, let's compare now frequency. So we will count the waves. We have 1.5. Over here we have 1, we have 2, 3, and 4. So frequency also changes between diagram 1 and diagram 2. Let's compare the amplitude. So the distance from rest position all the way to the crest. And you can see that amplitude here remains the same. And in the same way, since this wave is considered to be traveling in gas in the air, it means that the speed will also remain the same, which is the speed of sound in the air, 340 meters per second. So what is the only difference between diagram 1 and diagram 2? It's only the frequency and the wavelength. And this is logically speaking, that's because we just said in the previous slide that frequency and wavelength are inversely proportional. And so when we increase, so in fact here the frequency is low, but the wavelength is high. While here the frequency is high, but the wavelength is low. And so in order to change the pitch of the sound, we need to change the frequency, thus the wavelength will also get affected. So we can say that the lower the frequency, the lower the pitch, the higher the frequency, the higher the pitch of the sound. And this is the reason why a very heavy bell has a low pitch, while the reception small bell has a high pitch sound. Alright, so that's an example. Compare waves A, B, and C. In order to compare the waves, we need to compare their features, which are the amplitude, we have the frequency, we should compare the wavelength, and that's it. These are the main things that we need to compare. We won't compare the speed here, since all of them are considered to be sound waves traveling in the air, which means that they all have a speed of 340 meters per second. So let's start by comparing their amplitude, frequency, and wavelength. First thing, in order to compare the amplitude, we need to draw or to imagine where the rest position would be. Right? So this is not very accurate, but like if you compare, you can see that the amplitude is actually staying the same. It's not changing. So this, it stays the same. What about the frequency and wavelength? Now keep in mind, as we said, that frequency and wavelength are inversely proportional. So if you find that one is different, the other one must be different as well. Okay, so it's always easier to count the wave. So if we start by counting waves in A, this is 1 wave, 2, 3, and 4. And some of you will ask me, Miss, why you're starting from a crest and not from the rest position like in the previous question? Well, when you're starting from a position and you want to count one wave, you just need to repeat and end at the same exact position in order to say that this represents one wave. Okay, so in this case, since we're starting from a crest, then one cycle of a wave will also end at a crest. And this is why you will count 1 wave, 2, 3, and 4. So wave A has a frequency of 4 Hertz. Frequency of A is equal to 4 Hertz. Frequency of B is, we have 1, 2, 3, 4, 5, 6, 7, 8. So frequency of B is 8 Hertz, while frequency of C is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, around 16 waves that are going per second. Don't forget that we're counting the number of waves per second. And so now we can compare and say that C has the highest frequency and A has the lowest frequency, which means that C has the highest pitch and A has the lowest pitch. All right. What about their wavelength? The wavelength, as we said, it will follow the rule that since it's inversely proportional. And so C will have, since it has the highest frequency, it will have then the lowest wavelength, and A, since it has the lowest frequency, it shall have the highest wavelength. Okay? So you need to talk about the pitch of the sound. You need to talk about the loudness of the sound. In order to talk about the pitch, you should compare their frequencies. In order to talk about the loudness, you should compare their amplitude. So a simple way to answer this question would be, all three waves A, B, and C, they have the same loudness, okay? Since they all have the same amplitude. But since wave C has the highest frequency of 16 Hz, then it should have the highest pitch and it has the lowest wavelength. While wave A, which has the lowest frequency, has the lowest pitch and it has then the highest wavelength. Another exam style question for sound wave would be this. Here we have a display of a wave on an oscilloscope going in 1 second. And remember that since it's a sound wave in the air, of course, then the speed of the sound will be 340 meters per second. So question number 1 is find the frequency of this wave. Remember that frequency means that you need to count the number of waves that are going every second. And so here we need to simply count how many waves we have. This is 1 wave, 2 waves, 3 waves, 4.5. So the frequency in this case would be 4.5 Hertz. Question number 2 is what is the speed of the sound? Oh, I just answered this, so it's 340 meters per second. Why? That's simply because we are dealing with an example of a sound wave in the air. Now they want us to find the wavelength of this wave. Now, if we had a scale for each box represent how much in centimeter, then it would be easy to find the wavelength. You just need to count how many boxes we have, and knowing the scale, you would get the wavelength of the wave. But in this case, they did not provide us with a scale of the grid, and so we have to use the formula. Alright, so we know that we have this formula that is called very fluffy lamp. Velocity is equal to frequency multiplied by lambda, which represents the Greek letter of wavelength. And so in order to find lambda, we will rearrange the formula to find that it's equal to V upon F. And so it's 340 divided by 4.5. And the value of the wavelength would be 75.5 meters. That's a very long wave. Alright, now last question, question 4. How can we find the period? Period is always found using the frequency. There is no other way to find the period. Okay, so it's 1 divided by the frequency. That's 1 divided by 4.5 Hertz. And that will give you an answer of 0.22 seconds. Alright, now for echo, we want to understand what is an echo. An echo is a reflection of sound that arrives at the listener with a delay after the direct sound. So in fact, echo depends on the timing. The delay means the time at which the sound will arrive, let's say, back to our ear after a certain time. So an echo is actually a repetition of the sound. What really happened is represented in the picture. So the girl is sending a sound wave from her mouth. This is the source. And the girl is sending a sound wave that will soon hit a wall that is 165 meters away from her. After a certain time, her sound will echo backward all the way until it will reach her ear once again. So she will be able to hear her sound again after a certain time. In fact, if we want to find this time taken for her to hear her voice, we can use the normal formula of speed, distance, time. So we will say the speed of the sound is equal to the distance divided by the time. Now here, since we're talking about a sound wave, then the speed must be equal to what? To 340 meter per second, since we know that this is air. Now for the distance, you can see that the distance is given to us as 165 meter. But if we think about it, the voice, the wave, will travel from the source to the wall, and then this voice will echo backward and will travel again the same distance in order to reach the source once again. So this distance given to us is only the distance between the source and the wall. But for the wave to travel with this speed, the wave will travel double this distance. So the distance is equal actually to 330 meter. This is the distance that we can use. Now out of these given, what we need to find is the time. So we rearrange the formula in order to get time equals to what? So time is equal to distance divided by the speed. So it's 330 divided by 340. So the time is equal to 0.97 seconds. Echo is used by animals and humans through the process of echolocation. For humans, they send ships to the ocean in order to find the depth of the ocean. So to find the depth, a ship has a sensor that will send a sound wave, and then this sound wave will hit the seabed after a certain time, and it will reflect off until it returns back to the sensor/receiver. The ship will use the same formula, speed is equal to distance divided by time, but this time they use the speed of the sound wave in water, and they would like to find the distance. So they will say distance is speed times time, but pay attention that this time taken is for the sound wave to go from the source sender to the seabed, and then from the seabed all the way back to the receiver. So whatever they'll get, they'll divide it by 2, and they will get an approximation of the depth of the ocean. Same way, echolocation is used for orientation, obstacle avoidance, and social interactions for animals like dolphins and bats.